Welcome everybody. This is our second session in NEET previous year questions for chapter Atoms of class 12, and it has been quite long, around a month or more than a month that I have uploaded a video or any video. Actually, I was slightly busy with my family responsibilities. That's why uh, I had taken a break. So from now, I will try to be upload videos on regular basis. And again, if you find these videos helpful, useful, then show your appreciation by liking these, sharing these, subscribing to our channel, and if possible, then donating some amount by scanning the QR codes available. Now with this, let's start today's video. In the previous one, I actually don't remember now that up to which we have uploaded. So yeah, it looks this is the last question we have covered. That was question number 15. And now we will start with next question. That is question number 16. The ground state of hydrogen atom is minus 13.6 electron volt when an electron from its first excited state, its excited and excitation energy is. Now here it is mentioned that electron is in first excited state. Now for ground state for hydrogen atom or for any atom for ground state for hydrogen like atom, n is equal to 1, and for the excited state n is equal to 2. And for hydrogen atom, we know that E of n is equal to minus 13.6 by n square electron volt. So using this formula, we can calculate energy of the second state, second level or first excited state. So E2 will be equal to minus 13.6 divided by 4, and that will give us minus 3.4 electron. So now if we want this electron to get excited, what we need at least minus 3.4 electron volt energy, and we are considering here that that electron will go from second orbit to the infinite orbit, because here it is not mentioned that up to which level we need excitation. We go if we go from second to the third level, that is also excitation. And for that, let's check, even that is also possible answer. So for second, we know that is minus 3.4 electron volt, and for the third level E3 will be equal to minus 13.6 by 9, and that will give us 1.5, so minus 1.5 electron. And now if I calculate energy difference here between these two levels, that will come around that will come around minus 1.9 electron volt. So from second level to the third level for excitation, we need 1.9 electron volt, and that is not mentioned here. So the only possible answer will be 3.4 electron volt. That is option A for us. Now let's move to the next one. The total energy of electron in the ground state of hydrogen atom is given by this value, the kinetic energy of the electron in the first excited state. So again, here it is mentioned that we have first excited state. So we know the relation between kinetic energy and total energy, that kinetic energy is basically modulus of total energy. And our total energy is sum of potential energy plus kinetic energy, and from that we can also write that potential energy for any orbiting system, like here for the electron in classical system, it is 2 times of the total energy. So for the first excited state, here n will be equal to 2, and if n is 2, then energy of the second state, that is that I'm discussing regarding total energy. Total energy of the second state will be equal to minus 13.6 divided by 2 square, and this will give us minus 3.4 electron volt. So kinetic energy will be modulus of this, and that is option D for us. Let us move to the next one. The total energy of the electron in first excited state about minus 3.4 electron volt, it's kinetic energy. We just solved it, that kinetic energy will be modulus of the total energy, and that will be option A for us. Now in the next one, the Bohr model of atom assumes that angular momentum of electron is quantized. Use Einstein photoelectric equation, predicts continuous spectra, predicts same emission spectra for all type of atoms. Now we know that the core assumption of Bohr model, for Bohr model, that angular momentum of electron in the nth orbit Ln is equal to nh by 2 pi. That is the basically quantization of 2 pi. That is basically the quantization rule. So option A is right here. Moving to the next one. When hydrogen atom is in first excited level, its radius is. So we know that for the radius, we have the basic relation that Rn, and this is for the atom, not for the nucleus. Rn is equal to n squared times A naught, where A naught is the orbit radius of the first orbit. So for the first orbit, it will be A naught, and for the second orbit, that is the first excited level, it will be 4 times A naught. So radius becomes 4 times. So that is the 4 times, option A. Now remember that you have to distinguish here between the atomic radius, atomic radius and nuclear radius. For hydrogen-like atom, atomic radius is given by Rn is equal to n squared times A naught, where A naught is constant and its value is, I think, 1.5 angstrom. I don't exactly remember. And n is the, we can say, yeah, orbital number. Now for the nuclear radius, what we have relation, we have that radius of a nucleus is equal to R naught times A raised to power 1 by 3, where R naught is 1.2 Fermi, or 1.2 into 10 raised to power minus 15 meter, and this A is the nuclear mass, and which is a sum of proton plus neutrons. So you have to remember these two, and they are separate things. Now consider electron the nth orbit of hydrogen atom in the Bohr model. Circumference of the orbit lambda can be expressed in terms of de Broglie wavelength of that electron s. So here it is mentioned that nth orbit of hydrogen atom. So for the nth orbit, radius will be given by uh, n square times, let's say the constant, that is A naught. Now, this is the basic relation from the Bohr's principle. Now, it is mentioned that we have a de Broglie wavelength here. So, suppose this is the orbit. This is our orbit of the electron. Now, if electron has to exist as a wave, so what it has to do? It has to move like this. And if it has to move like this, then this number of waves, the number of total number of waves here should be integral multiple of the total length or the total circumference, or we can say that n lambda n, where n is the orbital number, lambda n is the wavelength corresponding to that orbital number. Suppose if we are discussing regarding fifth orbit, then we will write that 5 times lambda 5, and this should be equal to the circumference, and that circumference will be equal to 2 pi r n. So that is the basic relation. Now what we can do, we can substitute the values. So n lambda n is equal to 2 pi into n squared into A naught, that n gets cancelled, and from this we have lambda n is equal to 2 pi n times A naught. Now it is nothing is mentioned regarding which orbit we have to take. So let's write for the ground state. So for the ground state, what we will have? We will have lambda 1 will be equal to 2 pi times A naught. And okay, now I remember the value of A naught. It was 0.529 angstrom. 0.529 angstrom. I think I wrongly mentioned it here. Yeah, I mentioned it. wrongly. So it is 0.529 angstrom, not 1.5 angstrom. So now if I substitute this value here, what I will get? I will get lambda 1 is equal to 0.529 times 2 pi. And if I substitute it here, I will get? I will get lambda n is equal to n times 2 pi into 0.529. So this is the relation which I am getting here. Now, what we can do? We can do further substitution that lambda n, this is regarding de Broglie wavelength, will also be equal to n times the lambda node, where lambda node is the de Broglie wavelength of the ground state. So if I substitute it here like this, that n times lambda node is equal to n 2 pi into 0.529. Now n gets cancelled, and what we have? We have lambda node is equal to 2 pi into 0.529. But it still does not match with any of the given answer. So what we can do? Let us also write lambda node. Now lambda node is equal to 2 pi times r node. Now we can substitute it here, or 2 pi a node. Sorry, we are taking a node. So this will give us lambda n is equal to n times lambda. So basically this was the relation we are already using. So I think we have to devise it. We don't have to use it. So for that, what we can do? We can use this relation. Starting from this relation, I can write that for the ground state, lambda node will be equal to 2 pi times, and I have used here sometimes r, sometimes a, so bear with that. 2 pi times lambda node is 2 pi times r node, and for lambda n it will be equal to 2 pi, oh sorry, n lambda n will be equal to 2 pi times r n. Now n as it is, lambda n as it is, 2 pi r n is equal to n square times r node. And now if I divide both of these, what will I get? I will get n lambda n by lambda node is equal to 2 pi n square r node by 2 pi r node. R node get cancelled, 2 pi gets cancelled, and here n square gets cancelled. So what I will have? Lambda n by lambda node is equal to n. And from that I can write lambda n is equal to n times lambda. And that is the relation we are looking for. This is the relation in option D, where lambda is the wavelength for the ground state. So I think it will be clear to you. Now with this, let's move to the next one. To explain his theory, Bohr he used quantization of angular momentum, or quantization means basically conservation. So option B is right. Moving to the next one. Some energy levels of molecules are shown in the figure with their wavelength of transition. Then we have to find out relation between the wavelengths, that which wavelength will be higher or which will be the lower. So let me write. I think there is some problem. Yeah, it's working now. So we know that energy is basically hc by lambda, and from that lambda will be hc by E. So lambda, or the wavelength emitted, will be inversely proportional to the energy change. And here we can see that energy change, when energy change is highest, when E is highest, then lambda will be lowest, and when energy is the lowest, then lambda will be highest. Now let's find out the energy differences. So suppose this is level A, this is level B, this is level C, and this is level D. So energy difference between AP or EAP, that will be equal to, that is, this is basically minus 2.5 E. So that is, the difference is only 0.5 units. Now between AC, it will be 1 unit. Between AD, it will be 2 units. Now for B and C, it will be again 0.5 units. And for B and D, it will be 2.5 minus 4, that will be 1.5 units. And we have a last, that will be between C and D, and that will be 1 unit. So we can see that we have a 1 unit gap here, and we have a 1 unit gap here. So as both, for both of these transitions, energy gap or energy transition gap is same, so their wavelength will also be same. And similar for the these two levels, we will have same energy or same wavelength. So now let's start with the this lambda 3. For this lambda 3 is the transition between level A and level D, for which we have the highest energy. From A to D, we have 2 units energy change. So we have highest energy, so lambda will be the lowest. And if lambda is lowest, means lambda 3 will be the lowest. And here we don't have any such relation. So don't worry. But we know that lambda 3 will be the lowest. Now regarding lambda 2 is between A to C, and A to C we have 1 unit energy difference, so this has 1 unit energy difference. And B to D we have 1.5 energy difference. Lambda 1 is between B to D, and here we have 1.5 and unit energy difference. So lambda 2 has the lowest energy difference. For lambda 3, it was 2 units. For lambda 1, it is 1.5 units. So basically, we can say that lambda 2 is the highest, then comes the lambda 1, and then comes the lambda 3. So here it is mentioned that lambda 3 is highest, but we know that lambda 3 is the lowest, so option A is rejected. Similarly, B is rejected. Now coming to C, that lambda 1 is greater than lambda 2, that this is also rejected because lambda 2 is greater than lambda 1. So only we are left with option D, that lambda 2 is greater than lambda 1, and lambda 2 is 2 times the lambda 3. Now how we can find this? As lambda 2 has an energy difference of 1 and lambda 3 has an energy difference of 2. So lambda 2 will be twice. Using this relation, we can easily calculate that lambda 2 will be twice of lambda 3. So option D is the right answer here. Let's move to the next one. The spectra series which correspond to the electronic transition between the level 5-6 to the level 4 is. So this is basically regarding hydrogen atom. And we know that for hydrogen atom, we have different series. And let's start with Lehman. Then we have Balmer. Then we have Bastian. Then Brackett. And then we have P-Fund. Now Lehman belongs to when n is equal to 1, Balmer 4 and 2, Paschen 4 and 3, Brackett 4 and 4, and P-Fund 4 and 5. And these are the final levels that electron comes back to. So if electron is coming back to the 4th level, then it will be a Brackett series. So option B will be the right answer. Moving to the next one, given below are the two statements. Atoms are electrically neutral as they contain equal number of positive and negative charges. So yeah, that is right. Now statement 2, atoms of each element are stable and emit their characteristic spectrum. So statement 2 is wrong here because not each atom means not every atoms are stable. Why? There are some non-radioactive elements, non-radioactive, and there are some radioactive. These are stable ones because they don't decay, and these are the non-stable ones and they emit radiations. And there are type of these radiations are also, these are alpha, beta and gamma radiations. So statement 2 is wrong here, so 1 is right and 2 is incorrect, so that is option B. Moving to the next one, match the list 1 with the list 2. So spectral lines for the hydrogen for the transition from. So here we have to solve this. Now what we can do here, we can use slight shortcut. How? And we know this as these are for hydrogen atom only. So for hydrogen atom, and here we are transitioning from the second to the third, fourth, fifth, sixth levels. So for the second level, the energy is minus 3.4 electron volt. For the third level, and how we can calculate this? We can use formula minus 13.6 by n square electron. So for the third level, energy is minus 1.51 electron. For the fourth level, it is, I think, that will be minus 0.85 electron volt. And why I'm using this value and not using that standard formula that 1 by lambda is equal to R into 1 by n1 square minus 1 by n2 square? Because for that, in this scenario, calculations becomes difficult. Here, what I will use that lambda is Hc by E and Hc is 1240 electron volt nanometer divided by E. So let's calculate for transition lambda 23. So lambda 23 will be equal to 1240 electron volt by electron volt nanometer. Now energy difference between the level second and third, that will be equal to 3.4 minus 1.51, and that will be 1.89 electron volt. So electron volt gets cancelled, and when we solve this, we will get 656 nanometer. So A should go with third option. And if we see options here, we have only one that matches with A going with the third. So option A will be the right answer here. For the next one, in the hydrogen spectrum, the shortest wavelength in the Balmer series is lambda. The shortest wavelength in the bracket series is. So we know for the hydrogen atom, we have Lehman, Balmer, Paschen, bracket, and P fund. Here we have 1, 2, 3, 4, and 5. Now, shortest wavelength means the highest energy difference, and that is mentioned as lambda. So we know that 1 by lambda from the Rydberg formula is equal to 1 by n1 square minus 1 by n2 square. Now, as lambda is shortest, so we need highest energy difference, and highest energy difference will be when n2 is equal to infinite. So this formula reduces to 1 by lambda is equal to R by 1 by R by n1 square. So starting with the Balmer series. So for Balmer series, it is mentioned as lambda. So 1 by lambda is equal to R by n1 is 2 here for Balmer. So R by 4. Now for the bracket, let us mention as lambda b, it will be R by n is for bracket, n1 is for bracket, that is 4, so that will be 4 square or 60, and that can be written as 1 by 4 into R by 4, and that is 1 by 4 into 1 by lambda. So lambda b is 4 times lambda, and that is option D for us. Now in the next one, if an electron in hydrogen atom jumps from the third to the second orbit, it emits photon of wavelength lambda. When it jumps from fourth to the third orbit, the corresponding wavelength of the photon will be. Now, we know that energy difference between third and second orbit is greater than the energy difference between fourth and third orbit. And we also know that lambda is equal to hc by E. So lambda as energy difference between third and second orbit is higher than the energy difference between fourth and third orbit. So lambda for the fourth and between fourth and third orbit will be greater than the lambda between third and second orbit. So from that, this option is rejected as here wavelength or value of wavelength is reducing as 9 by 16 is less than 1. Similarly, option A is also rejected. Here it is 16 by 25, that is also less than 1. So A and B both are rejected. Now coming to the actual calculations. So 1 by lambda will be equal to, and that is 1 by lambda 2 3 r 1 by 2 square minus 1 by 3 square. So from this, what we will have? We will have lambda 2 3 is equal to 36 by 9 minus 4, that is 5. And similarly, 1 by lambda 4 3 will be equal to r 1 by 3 square minus 1 by 4 square. And from that, lambda 4 3 comes out to be 7r by 144. 7r by, oh sorry, I think, yeah, 144 by 7r. 144 by 7r. Now what I can do, I can split as 36 into 4 is 24, 12, 144. So yeah, so this can be written as 4 into 36. Here I have 7, here I have r, and we need 5 here separately. So multiply 5 and divide 5. So this will be equal to the lambda 2 3. So this will become 20 by 7 into lambda 2 3. So that is option C for us. Moving to the next one. Now in the next one, the transition from N3 to N1 is of the hydrogen atom falls in UV radiation or UV region. Infrared radiation will be obtained from the transition form. So we know that energy for UV radiation is basically greater than the energy of infrared. In the spectrum of the visible of the EM radiations, we have UV, then comes out the visible, this is reducing energy, and then comes the infrared. Infrared has the lowest energy. And we also know that for hydrogen like element, suppose this is first level, sorry, n is equal to 1, then we have the second level, then we have the third level. And here one thing to be noticed, that we have to notice one thing, that this energy difference between first and second level is higher than the difference between second and third level. And similarly, difference between second and third level is greater than the difference between third and fourth level. So as we move up, the difference between the energy levels reduces, and as difference between energy levels reduces, so lambda, that is given by hc by E, increases. As E reduces, lambda increases. And we know that lambda for infrared is greater than lambda for UV. Why? Because energy of the UV is greater than energy of infrared, and energy and lambda are inversely related to each other. So if we are getting UV light between third and first transition, means this transition is giving us UV radiation, then the only possible chances for infrared will be, might be between 2 and 3, might be between 2 and 3, and might be between this is fourth level, between fourth and 3. Now highest chances will be between fourth and 3. Why? Because here we cannot guarantee that energy level has reduced that much that it now falls in the infrared, but here we can surely say that these levels will have energy, such a low energy that they will give us infrared. So between fourth and 3 is the most viable answer. Yes, It is also possible, this answer is also possible between 3 and 2, but if we have to mark it with more surety, more confidence, then that will be between 4 and 3 levels. So that is option D for us. Moving ahead. Electron in hydrogen atom first jumps from the third excited state to the second excited state. So third excited state means n is equal to 4, and second excited state is n is equal to 3. And then from the second excited to the first excited state, the ratio of wavelengths. So how we can do? Now wavelength is 1 by lambda is equal to r times 1 by n1 square minus 1 by n2 square. So between fourth and third, it will be 1 by lambda 4 3 is equal to r 1 by 3 square minus 1 by 4 square, and from this lambda 4 3 will be 144 by 16 minus 9, that is 7r. Now for the uh, second and first excited state, so that will be second excited state is 3 and first excited state is n is equal to 2. So 1 by lambda 3 2. This will be r 1 by 2 square minus 1 by 3 square, and from this lambda 3 2 is will be 36 by 5r. I think we have just solved this type of question, and the answer was 20 by 7. I remember just now, and here it was, that is 20 by 7 lambda 2 3, that is was lambda 4 3. So you can do the remaining calculation, and from that you will find that lambda 4 3 is 20 by 7 times of lambda 3 2. That is option D for us. Moving ahead, monochromatic radiation emitted when electron on hydrogen atom jumps from first to the ground state irradiates photosensitive material. The stopping potential measured to be 3.57 volt. Threshold frequency of the material is. So it is mentioned that electron is emitted by the radiation, and that radiation has come from the second state to the first state transition. So for the first state of hydrogen atom, we have energy minus 13.6 electron volt, and for the second we have minus 3.4 electron volt. So the energy difference or the photon emitted will be equal to of 10.2 electron volt energy. Now this is the energy, so from that we can calculate the maximum kinetic energy of the emitted electron. This is the energy of photon emitted from the transition between the second and first level of hydrogen atom. Now this will strike the metal plate and it will eject electron. Now for that electron we can use photoelectric equation, that E times Vs, where Vs is the stopping potential, is equal to energy of the photon minus the work function, and that will give us, and both of these two are in electron volt, so this will give us 6.63 electron volt is equal to EVS. Now from this stopping potential is 6.63 volts. Now we have to calculate the threshold frequency. Oh, sorry, my mistake. I got carried out. It is given, this is the stopping potential. So actual equation will be like this. Let me write this. This will be phi, or the work function, because actual equation is EVS is equal to energy of the photon minus work function. This is given to us. This is we have calculated. So from that work function comes out to be 6.63 electron volt. Now from that we can calculate the threshold frequency, and that will be equal to phi is equal to basically h nu. So frequency will be phi by h. Phi is 6.63 electron volt, and we will convert into joules. So multiply 1.6 into 10 h power minus 19 divided by h, that is 6.636 10 h power minus 20 minus 34. So assuming these to be equal, so what we will get 1.6 into 10 h power minus 19 plus 34, that will be 10 raised to power 15. So approximately our answer will be option C. Moving to the next one, an electron in the hydrogen atom jumps from excited state N to the ground state. The wavelength so emit eliminates a photosensitive material have a work function 2.75 electron volt. The stopping potential is 10 electron volt, the value. And so we know that E times Vs, that is stopping potential, is equal to energy of the photon minus work function. So here stopping potential is 10 electron volt. So 10 electron volt is equal to energy minus work function, that is 2.75 electron volt. So from this we can calculate energy of the photon that strikes on the metal plate or photosensitive material, that is 12.75 electron volt. Now this energy has to be the difference between the two levels, and as this is for the ground level, for the ground state, we have minus 13.6 electron volt. So this transition is basically happening from the nth level to the first level, which is also mentioned in the question. So we can write that uh, as we know that delta E will be here equal to modulus of E1 minus En. So if I write it in a properly formatted manner, that will be 12.75 electron volt is equal to 13.6 energy of the first level minus 13.6 by energy of the 13.6 by n square, that is the energy of the nth level. So from this we will get 13.6 by n square is equal to difference of these two, and that comes out to be 0.85. And from that n square is 13.6 by 0.85, which is approximately equal to 16, and from that n comes out to be 4. So option B will be the right answer. Moving to the next one, out of the following which one is not a possible energy for photon emitted by the hydrogen atom according to the Bohr model? So we know that energy for the first level is minus 13.6 electron volt. So maximum energy of the emitted electron can be 13.6 electron volt. So all options are possible according to that. Now let's move to the other levels. So for the second level we have minus 3.4 electron volt. For the third level, we have minus 1.51 electron volt. For the fourth level, we have negative 8.85 electron volt. And E5 will be negative 0.55 electron volt. Now, if we take transition between first and fifth level, then that will be approximately equal to 13.1. So we can say option C might be possible. Now, let us move to if we take energy difference between first and third, that will be 13.6 minus 1.51. So that will be 12.09. So 12 is possible, and between first and second we have 10. So option B is not going to be possible here. For option D, we have 0.65 energy difference, that is possible between third and fourth. And for 1.9, that is possible between second and third. So we can say option B is not possible here. Now 34th, the wavelength of the first line of Lehman series for the hydrogen atom is equal to the second line of the Balmer series for hydrogen-like ion. The atomic number Z for the hydrogen-like ion is. Now for the Lehman series, N1 is equal to N1 will be equal to 1, and this is the for the first line. So let us write it as 1 by lambda h. This is the transition wavelength for the hydrogen atom for the first Lehman line. So that will be equal to R by 1 by n square, 1 by 1 square minus 1 by 2 square. So 1 by lambda h will be equal to R into 1 by 1 minus 4, 1 minus 1 by 4. So that will be 3 by 4. And from this lambda h is 4 by 3R. Now for hydrogen-like element, suppose that is 1 by lambda z, and it will be equal to n square times r, sorry, z square times r. And this is regarding second line of Balmer. So for Balmer, n1 is 2, so 1 by 2 square, and that is also second line, so third, fourth level, and this will give us z square 1 by 4 minus 1 by 16. What we can take? We can take 4 common, so that will be z square by r divided by 4, and we will have 3 by 4. So these two are equal. This and this, these two are equal. So r into 3 by 4 is equal to z square r by 4 into 3 by 4. So 3 by 4 and r get cancelled. Z square is 4, z is plus minus 2 or 2. That is option 2 for us. Now let us move to the next one. Ionization potential of hydrogen atom is minus 13.6 electron volt. Hydrogen atoms in the ground state are excited by monochromatic radiation of energy 12.1 electron volt. According to both theories, spectral lines emitted. So number of spectral lines emitted. So initially electron is in level with 13.6 electron volt, then it get excited due to some radiation and goes to a level, takes energy of 12.1 and goes to some level, and energy of that level will be 13.6 minus 12.1 because electron absorbs that energy, or basically in actual calculation actual energy of electron is negative, and when it absorbs that energy, that it adds up, so that will becomes minus 1.5 electron volt, and this is the energy related to the third level, E3, for hydrogen atom. So we have to find out number of spectral lines. Now we know that number of spectral lines are given by n into n minus 1 by 2. So here n is 3. So 3 into 2 by 2, that is 3. So number of emitted spectral line can be 3. So that is option C. Moving to the next one, energy levels A, B, C of the certain action corresponding to increasing value of energy, that A is the lowest energy, B is middle, and C is the highest energy. If lambda 1, lambda 2, and lambda 3 are the wavelength of the radiation corresponding to C to B, B to A, and C to A respectively, which of the following relation is correct? Now, let me draw the schematic diagram. So C, level C has the highest energy. So let this is EC, then we have EB, and then we have EA. Lambda 1 is the wavelength from C to B. So this is lambda 1. B to A, that is B to A, that is lambda 2, that is lambda 2. And C to A, that is lambda 3. Now we know that lambda is given by HC by E. This is the relation we have, and from this we can write 1 by lambda is equal to E by HC. Now let me write for the lambda 3. So 1 by lambda 3 will be equal to, this E is the energy difference, so that will be equal to EC minus EA by HC. And now I can modify it slightly. EC minus EB plus EB minus EA by HC. Now, if I separate these terms like this, this will be energy difference between level C and B by HC, that is equal to lambda 1. So 1 by lambda 3 is equal to 1 by lambda 1 plus 1 by lambda 2. And from this I can write lambda 3 will be lambda 1 lambda 2 by lambda 1 plus lambda 2. That is option B for us. So option B is the right answer here. Now let's move to the next one. Energy E of the hydrogen atom with principal quantum number is given by this relation. Energy of a photon ejected from the level N3 to the N2 of the ground state of the hydrogen approximately. So for the third level, we know energy is minus 1.51 electron volt. For the second level, we know that is minus 3.4 electron volt, and their difference will be equal to minus 1.9 electron volt. So basically that is option D for us. In the next one, electron jumps from fourth to the second orbit, as final orbit is second, so this will be a Balmer series with second line. So option B will be the right answer. Moving to the last one for this one, the spectra obtained from sodium vapor lamp is an example of. So as we have, it is a sodium lamp. So how it operates? So what we do, we provide electricity which heats the filament, and when that filament is heated, it emits light. So this is a basically emission spectrum. That is option C for us. So with this video is complete, and this chapter is also complete. Hopefully you will find it useful. If you have any doubts, suggestions, anything extra or anything, you can put them in comment section. Like this video, share it as much as possible, and if you like to donate, scan these QR codes. We will meet in the next chapter. Thanks for watching.